Hello everyone and welcome to this video of the course Robotics. In this video we are going to discuss about the topic serial communication with Arduino. The content covered in this video will include serial and parallel communication, synchronous and asynchronous communication, baud rate, and we'll be looking at how do we do serial communication with Arduinos and the command used for doing serial communication with Arduinos. First, let's get started with the serial and parallel communication. In case two devices are communicating and the data bits from device 1 to device 2 are being sent through a single channel one by one, that sort of communication is called as serial communication. And in case data bits are sent from device 1 to device 2 and there are 8 parallel channels and data bits are sent all together at a time, that sort of communication is called as parallel communication. As shown in the image, the above one, there is only one channel between the device 1 to device 2, so data bits are sent one by one and all data bits are not received at the second device at a time. So this sort of communication is called as serial communication, and in the below image it is shown that from device A to device B, or let's say device 1 to device 2, we are having around 8 channels and 8 data bits are sent all together at a time and received at a time. So this sort of communication is called parallel communication. Generally, we prefer doing serial communication because serial communication requires less number of wires and is economical in terms of doing long range communication. Talking about the basic differences between serial and parallel communication, some of them would be: in serial communication, only one data bit is transceived at a time because there is only one channel between transmitter to receiver and receiver to transmitter. Whereas in parallel communication, multiple data bits are transceived at a time. Because of only one data bit transceived at a time, it will take more time for complete data byte to be received, so serial communication is slower. Comparatively, parallel communication is quite faster because multiple data bits are transmitted at a time. So byte by byte transmission is done, whereas in serial communication, bit by bit transmission is done. The benefit of using serial communication is, in serial communication you need less number of cables to transmit the data, whereas in case of parallel communication, you will need higher number of cables to transmit the data between one device to second device. So in most of the use cases now, serial communication is more preferred over parallel communication because of the less number of required cables, which makes it more economical compared to parallel communication. So in this course, we are also going to use serial communication while communicating between Arduino and PC or Arduino and Android smartphone as well. Again, in serial communication, there are two types of communication interfaces. One of them is synchronous serial interface. A synchronous serial interface always pair its data line with a clock signal, so all the devices on a synchronous serial bus share a common clock. Or you can say, all the devices on a serial bus communicating with each other are communicating on a common clock signal. This makes for a more straightforward, often faster serial transfer, but it also requires at least one extra wire between the communication devices. For example, if device A is communicating with device B and both of them have different inbuilt clock speeds, then they can share a common clock using one more extra wire. So synchronous serial interface increases one extra wire, one extra cable for communication, which is used for sharing the common clock. There are several synchronous serial interfaces like SPI, that is serial peripheral interface, and I2C, that is inter-integrated circuit, which is also called as TWI, that is two-wire interface. These two are synchronous serial interface protocols which is widely used in industry for communicating sensors and some other microcontrollers with programmable systems and microcontrollers. There's another interface that is called asynchronous serial interface. An asynchronous serial interface means that data is transferred without support from external clock signal. It means the two devices communicating with each other do not share a common clock. So this transmission method is perfect for minimizing the required number of wires and input-output pins. But here also it does mean that we need to put some extra effort or some extra rules into reliably transferring and receiving data. For that we use a technique called Baud rate, which we'll be discussing in further coming slides. So in our case we are going to use asynchronous serial interface for this course. For an asynchronous serial interface, the serial bus consists of just two wires, one for sending data and another for receiving data. So that is transmitter for sending data and receiver for receiving data. As such, serial devices should have two serial pins, the RX that is receiver and the TX that is transmitter. So for device A and device B to communicate with each other, the RX of device A will be connected to TX of device B, and the RX of device B will be connected to TX of device A, and they'll be sharing a common ground as well. A serial interface where both the devices may send and receive data is either full duplex or half duplex. Or you can also call there are two types of serial communication. One of them is full duplex and another is half duplex. Full duplex kind of serial communication is the communication where both the devices can send and receive data simultaneously. Whereas the half duplex communication is the type of serial communication where the serial devices must take turns while sending and receiving data. So at a time only either sending or receiving of data can be done. Coming back to the term that is baud rate, we have seen that in case of asynchronous serial communication, there should be some extra effort to be put for reliable transmission of data. For that case, we use a term called baud rate, that is the rate at which the data is being transferred, or you can say the rate at which either transmitter is sending the serial data or the receiver is receiving the serial data. If the rate at which transmitter is sending the serial data or transmitting the serial data is same as the rate at which the receiver is receiving the serial data, then the data bit sent by transmitter will be understood easily by the data bit received by receiver, and if the baud rates are same, the communication will be reliable and proper. If the baud rate differs, the communication may have some errors. So generally we work with standard baud rates for communication between two devices, and the standard baud rate, which is generally supported by most of the microcontrollers and computers, is 9600 bits per second. In our case also, we are going to use the serial communication baud rate as 9600 bits per second. In case of Arduino, we'll be doing serial communication between Arduino and PC, and for that we'll be using the same USB cable which we generally used to upload a program to Arduino. In general case, on Arduino Uno, the pin number 0 and pin number 1 has serial interface which is multiplexed with the USB cable, and the same serial interface is used to upload the program to Arduino Uno. So we'll be passing data via this serial cable to Arduino Uno for exchange of information. Generally, the information is transmitted as zeros and ones, and also known as bits, between the two devices, which could be your computer or Arduino Uno. In case of Arduino Uno, we have the two LEDs on Arduino, that is TX and RX LED. So whenever the Arduino is transmitting any data, the TX LED on Arduino will glow, and whenever the Arduino is receiving any data, the RX LED on Arduino will glow. Whenever you compile any program in Arduino, the compiling turns our program into the binary data, that is 0 and 1, the set of 0101 data. And when we upload the program, then originally our computer or the Arduino software sends the serial data through the USB cable into the Arduino, and you might analyze that RX and TX LED on the Arduino will glow while uploading a program to Arduino. So the two LEDs nearby the USB connection blink when the data is transmitted or received. The RX LED will blink when the Arduino is receiving data, whereas the TX LED will blink when Arduino is transmitting data. In Arduino, for doing serial communication, it is must that we have to declare the baud rate before either transmitting or receiving the serial data. For declaring the baud rate, the command or the syntax used in Arduino is serial.begin. Inside the serial.begin, the parameter that we pass is the baud rate. So you may pass CL.begin 9600 as the parameter, which is the baud rate of us. For sending the serial data, we generally use the syntax cl.print. In case we want to send new line as well, we can use cl.println and pass the parameter of the variable which we want to send. For reading the CL data, we can use cl.read in Arduino Uno. So these are the basic commands, and we'll be using further these commands to communicate between Arduino and PC in coming videos, and to also interface HC05 Bluetooth module as well with Arduino Uno. So stay tuned for further videos. We'll perform some hands-on practical related to serial communication in next coming videos. Thank you for watching this video.